Chapter 11 and 5 in complex power. In previous, we are discussing about the power in the time domain. So, this is element, and there are voltages up here, and the current is I. Then power T is Vt and It. We call there is an instantaneous power. In Korean, 순시 전력. And especially when the V voltage and current is periodic waveform, then we can define in the average power was this is the average power, and then in the case of the voltage and current is sinusoidal, then F Vt is Vm cosine omega t plus theta V, then current It is Im cosine omega t plus theta I. Then the instantaneous power of this is Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine 2 omega t plus theta V plus theta I. And we said, this term is average power. So we call this as instantaneous power. And in chapter 11, chapter 10, to analysis the sinusoidal AC circuit, we have used the phasor. So we redraw this circuit here. There is V omega and I omega. Then these time domain, the variables, can be represented in the phasor. V omega was magnitude and phase angle theta V, and current phasor was magnitude and theta I. Then we want, actually this is a kind of a complex number. So this can be represented. This is a polar form, and we can represent this phasor in the rectangular form. There will be Vm cosine theta V plus J Vm sine theta V. So current can be represented in the same manner. Actually, this is a complex number. The phasor is kind of a complex number to represent the sinusoidal variables in the magnitude and their the phasor angle. So based on here, based on these page values, I want to calculate the power. So, this can be represented in other Vm exponential j zeta v, and that was Im exponential j zeta I. Oh, no, we right here. These variables are complex number. Then the newly defined the complex power S is defined in this way. On the path V and current conjugate, we call this is a complex power. We define the complex power in this manner. So this is represent the power in the viewpoint of the pager when the voltage and current is sinusoidal. This is very useful and this is very powerful to gather the characteristic of the electric circuit according to the power. So we rewrite the complex power. We define complex power is S. S is V pager and current conjugate. So that is Vm zeta V and Im zeta I conjugate. So that will be Vm zeta V and Im minus zeta I. So it will be half of magnitude of voltage and current, and phase angle is zeta V minus zeta I. So here we have defined the another variables. So the magnitude of S compressed power defined that will be Vm Im divided by 2. We call this apparent power. In Korean is 피상전력. This is another new definition of power. In Korean, the value is 복수 전력. Then we can change the complex power in other forms, because S is Vm Im divided by 2 zeta V minus zeta I. They can be represented in the rectangular form. was Vm Im over 2 cosine theta v minus theta I plus j Vm Im over 2 sine theta v minus theta I. So because the voltage and current in the phasor is complex, so the complex power is also complex number. So we can represent this is P plus JQ. P is a term of the real term of the complex power, and Q is the imaginary component of the complex power. So we rewrite S is P plus JQ. Here P is Vm Im divided by 2 cosine theta v minus theta I, and Q is sine theta v minus theta I. And so we call this P is active power. In other words, in Korean, 유효. And this component is Q. This is we call reactive power. In Korean, it's 무효전력. So in the case of sinusoidal circuit, the effective power and average power and active power is the same values. I mean, definition is different. Effective power and average power and active powers have different definition. But in the case of sinusoidal AC circuit, the quantity, the quantity of effective power, average power, and active power is the same. The effective power is, Korean is 유효. This is 평균. The name of active power is 유효. So you remember that you see the time domains. What is that? 1/2 here. 1/2 Vm Im cosine theta v minus theta I. In here, 1/2 Vm Im cosine theta v minus theta I. It's the same variables. So in time domain is the average power. It's the same with the phasor in P, active power. The same quantities. So we need to represent in the voltage and current in the several ways. Okay, if for example Vt is the Vm cosine omega t plus theta v. And what's the meaning of that? That means Vt looks like here. Looks like this. Oh, sorry. If this is a Vt, then this is a phase angle. Actually, if we represent this is time domain, then that time is, we call this a t0. Omega t0 will be theta v. Therefore, t0 will be theta v divided by omega. So, and that value is Vm. Therefore, this waveform minus Vm to Vm variation. And the frequency of that is omega divided by 2 pi is frequency. This is waveform. When you know that, so what is the RMS values of this? This is RMS value is VRMS is, how can you get that? The effective value is RMS values. 1 of t, 0 to t, Vm cosine omega t plus theta v dt. Okay. Square. And del result to calculation, del result will be Vm, the peak values divided by root e. Therefore, peak value is root e v RMS. So I will rewrite the Vt. And if you represent Vt is a magnitude value in peak values, Vm cosine omega t plus theta v, then we also represent instead of Vm V RMS cosine omega t plus theta v in this manner. So in the same way, if we represent current, It is Im, the magnitude values, cosine omega t plus theta I, then this can be represented in the RMS values. So then root E I RMS cosine theta omega t plus theta I. So we have several represents of the voltage and current in this manner. Okay. First, I want to represent the voltage here. Voltage in the peak values. Or I can represent this is RMS values. Then VT is maybe VT is magnitude of voltage and cosine omega t plus theta V. Then that can be represent as V2 EV RMS cosine omega t plus theta V. Unit of this is watt. Oh, no watt is volt. Then current IT, if represented IT is magnitude Im cosine omega t plus theta I, then IT can be represented in the phasor value, RMS values. Then root 3 I RMS cosine omega t plus theta I. Unit of this is ampere. Then I can calculate the complex power S. Then S can be represented in the peak values as Vm Im divided by 2 cosine theta V minus theta I plus Ch2 Vm Im. Sorry, is it so? Yes. And plus Ch Vm Im sine theta V minus theta I. Then complex power also represented in the RMS values. Here is Vm is square V RMS and Vm is 2 I RMS and divided by 2. Therefore, eliminated. In this way, therefore, we'll remove it. What is the remain? The answer is remain. So we can rewrite V RMS I RMS cosine omega theta V minus theta I plus J V RMS I RMS sine theta V minus theta I. Unit of this is volt ampere. Then you can represent the apparent power. There is a magnitude of complex power. So that is the magnitude of the Vm Im divided by 2. If you represent this value in RMS, then apparent power is V RMS I RMS. Then we can represent the active power. In the case of sinusoidal, then active power or average power or effective power is the same variables. In Korean is 유효전력. P is Vm Im over 2 cosine theta V minus theta I. So P can be represented in the RMS values. V RMS, I RMS, cosine theta V, I'm sorry, minus theta I. Actually, unit of the apparent power is voltage in ampere, VA. In the case of the active power is watt. The only real thing is reactive power. 무효 전력. Q means Q is Vm Im over 2 sine theta V minus theta I. And Q also represented in the RMS values in V RMS sine theta V minus theta I. The unit of that is VA, reactive means R, the VAR. VAR is a unit of the reactive power. So here, so as you see here, what is better to represent it in the voltage and current? When you represent the voltage and current, the peak value is more simple because Vm cosine, Im cosine, that's it. But in the viewpoint of the power, what is better to represent is simply RMS is more simple. VRMS, IRMS, VRMS, IRMS, VRMS, RMS, VRMS, IRMS, VRMS, IRMS. So generally in the AC system, the RMS is more used frequently because it's a little bit simple. So when you say the outlet voltage is 220 volts, that means that is not peak values, that is RMS values. So I review here in the viewpoint of the RMS, viewpoint of the pagers and the complex power. We want to see the impedance with regard to complex power. Here, this is a voltage Vt, and this is current It. Then this can be represented in the pager. We have V omega, I omega, there will be G impedance, G. Then Vt is Vm cosine omega t plus theta V, and It is Im cosine omega t plus theta I. And this can be represented V omega is Vm theta V, and I omega is Im theta I. So from here, the complex power was Vm Im cosine theta V minus theta I plus J Vm Im over 2 sine theta V minus theta I. So here we are discussing about the G impedance. G. What is Z? There is a ratio of voltage pager and current pager. So the two here is Vm theta V divided by Im theta I. There will be Vm over Im phase angle theta V minus theta I. You know that when you calculate the power, that angle is theta v and theta I. And then you know that the impedance's angle, phase angle, is theta v minus theta I. This is important. So this impedance can be represented in the rectangular form. There will be Im, Vm over Im cosine theta v minus theta I plus J Vm over Im sine theta v minus theta I. So we call, now as you know, this term is related to the, okay, this is a P plus JQ. I mean, this term is related to the P, and this term is very related to the Q. So we call this is R plus JX. Here R is an active power consuming device, so we call this is resistance. And X is kind of a reactance. So as you see here, in the active power consumed by resistor, this is related to the active power. And this X is reactance is related to the reactive power. This R is caused only by only resistor, and the reactance X caused by inductor or and capacitor. So, and especially we call the theta v and theta I, we call this is a load angle. And this is very similar here. We call this is load angle. So now we want to represent the active power okay, here represent as complex number, complex power represented by Z impedance. Then let's add the S is Vm Im cosine theta v minus theta I plus J Vm Im divided by 2 sine theta v minus theta I. Now, to represent the impedance G, so we change that as, I mean, this is the impedance, this is the impedance. So we represent, this term is like in this way. Im squared 2 Vm Im cosine theta v minus theta I plus J Im squared Im Vm sine theta v minus theta I. Then that is, that is kind of a, here G was Vm Im cosine theta v minus theta I plus J Vm Im sine theta v minus theta I. Therefore, this term is a real part over here, real G, and this part is the same way, imaginary G. Therefore, we rewrite here is this is real of G plus J is Ch11-2 imaginary G. So therefore this is a P plus J, this is a Q. Therefore we can say that P is a real G and Q is here. So as you see, the active power is related to the real part of the G, and the reactive power is related to the imaginary part of the G. So we rewrite this is when your G is R plus JX, therefore this is R and this is X. Therefore R is R plus JX is 0. Here X is a 0 case. When L in L case, GL is R plus JX. And here R is 0 and X is omega L. So we can draw these, the active power and reactive power in the viewpoint of the complex plane. So if we draw, if you draw the complex plane here and here, this is a active G and imaginary G, and you define this is a G, then there is R and there is X. We say this is a theta. Here theta is the V minus theta I. That also we can represent in the same form here. And this is a real S. That means P is an imaginary S. There's a Q. So this is S, this is P, and this is Q. So this is a theta. This is also the load angle theta, the same things. This is an example to discuss about the complex power in the 11 and 5 and 1. We have a lattice here. This is a current source, so IT, and current source is connected in the resistor and one inductor in parallel. So This is R and this is L. Then IT was 1.25 and cosine 5t minus the 15 degree ampere here. We have two problems. First problem is when R is 20 ohm and L is 3 Heli. In this case, what is complex power? Okay, so to get here, we need to simplify this circuit here. And this circuit can be represented as one pager, one pager and one impedance. And this is a parallel GR and GL. And here omega is 5, therefore I is 1.25. Is I phase is 1.25 minus 15 degree. So first I will make an impedance, then G was the parallel with GL and GL. So that is 1 over GR plus 1 over GL and the inverse. GR is R and GL is J. Omega is 5, L is L. Therefore J 15. This is 20. So that will be 1 over 20 plus 1 over J 15 in inverse. And that will be 20 plus J 15 and J 15 and 20. So there will be, you can calculate with the calculator, is 7.2 plus J 9.6. So you can represent it in the polar form as 12 and phase angle is 53.13 degree. So I want to calculate the voltage. This is a voltage V. And V is I ohms. This is IZ. And here I is 1.25 and minus 15 degree, and G is 12 and 53.13 degree. So that will be result is 15 and phase angle is approximately is 38 degree. So we can calculate complex power. Definition of the complex power S is half V pager and current pagers the conjugate. So there will be half 38 degree and current is 1.25 and minus 50 conjugate is 15. So the result is 9.375 and phase angle is 53 degree. The unit is voltage ampere, VA. So we can rewrite this as a polar form here. There will be 9.375 cosine 53 degree plus J 9.375 sine 53 degree will be 5.643 plus J 7.487 VA. This is a P. This is a P, active power, and this is a reactive power Q. The unit is watt. Is var. I mean that is consumed by resistor. That is related to the resistor. And this is related to the L. So this is complex power. And second problem is a little different. Second problem is in this case we have complex power in 11.72 plus 11.72. And to generate complex power in this way, we need to determine R and L values to generate this complex power. So at first we need to know the voltage. So the relationship between complex power, S is half VI conjugate. Therefore, V complex power is twice divided by current conjugate. So we know that the 2 and S will be written here, and the polar form is 16.57 and phase angle is 45 degree. You can use calculator to get these variables. So 16.57 and 45 degree divided by current conjugate is 1.25 and phase angle is minus 15, but the conjugate is plus 15 degree. So voltage here is 26.52 and phase angle is 30 degree. It's simple. Therefore, impedance G is a V divided by current, and V is 26.25 30 degree, and current is 1.25 minus 15 degree. So the calculated result is 21.21 and 45 degree. This is impedance of RL parallels. So what that is that? That is 1 over R plus 1 over J. Omega is 5 and L inverse. Therefore, 1 over minus J 5L is 1 over 21.21 45 degree. That will be 0.0333 minus J 0.0333. This is 1 over R and this is 1 over 5L. Therefore, R is thorium and L is 6 He. So this is a way to calculate complex power, and or reverse from the complex power we can design the impedance in R and L. Another example 11.5 and 2. Here we have a circuit like that, voltages, and we have two impedance. I don't know what is that. But anyway, we have two impedances here. Because defined impedance is A, and this is B, and this is a VT. So VT was 24 cosine 5t plus 30 degree. Then compressed power consumed by impedance A was 9.216 plus J 6.912. It is VA. And the impedance B was defined 42.426 and phase angle is 45 degree. Here at first we should is determine the compressed power. So to do that, we need to know the GV. That's the first. So we know the GV, but we need to know. we need to know the compressed power consumed by GB. So to do that, at first, we need to know the current. We define this as current is I, and define this current is IA, and the current is IB. So we can calculate the IA at first. SA is half VA and IA conjugate. And actually, the VA is the same with VB, the same with V. That is 24 and 30 degree, and omega is 5. So IA is kind of a 2SA divided by the V conjugate. So we insert all variables 2, and VA is, and SA we calculate that is 11.52 and 36.9. So this is 11.52 and 36.9 degree, and 24 and 30 degree as a conjugate. So there will be 0.96, angle is -7 degree. And what is IB? IB is simple. V divided by GB. The V was 24 and 30 degree, and GB is 42.426 and 45 degree. So that result was 0.566, angle is -15 degree. Therefore, we can calculate I is IA plus IB. So we can calculate I is 0.96 -7 degree plus 0.566 -15 degree. The result is 1.522 and -9.9 degree ampere. So what can we do to determine the compressed power? So the supplied by the source compressed power is half VI conjugate. Therefore, half V was 24 and 30 degree, and current is 1.522 in degree. So then results can be calculated very simple. Is 18.264 and angle is 39.9 degree. This is a free A. Or we can have another solutions, because we know that the GV, therefore we can calculate IB directly. How can you do that? In the IB, IB is V divided by GB. Then SB is half V and IB conjugate. So there will be half and V and okay, V was 24, 30 degree and IB was 24 and 30 and GB was that values 24 and 42.426 and 45 degrees conjugate. So we can use it. So that will be 12, 30 degree and 0.566 and angle is minus 45, but this conjugate plus 15 degree here. So calculation value is 6.788. The phase angle is 45 degree. Therefore, could be .8 plus J 4.8. Therefore, S is the sum of SA plus SB. When SA was here 9.216 plus J6.912 plus SB is 4.8 plus J 4.8. That will be 13.016 plus J 11.712. So the result is very simple. So you remember that, you already discussed about here. I think this is more simple. Oh, I have a long numbers. This is not 3, 1, 3. This is 14. Okay, that value is 14.012 and plus J 11.713. So you know that their result and same with their result. So two methods is the same. This approach we calculate supply the complex power from the source, and we calculate this is constant power by the impedance. And number B is determined the equivalent impedance. It's a very problem because we know that V and I, there's a V and I, and V was defined in 24. These are givens, and the current is calculated in this way here. So 1.522 and minus 9.9 degree. So there'll be 15.768 and 39.9 degree. This is impedance. So we need to know here is, in this case, the supply from this source is power is some way that the provide this impedance and this impedance. So we can you can summarize that as the sum of the complex power received by all elements over circuit is always 0. That means all Vk Ik conjugate it will be 0. That means all active power is 0 and all reactive power is 0. This is another example. Example is 11 and 5 and 3. So we have circuit here. So Vt, and define this current is It, and there are series resistor and inductance, and there are capacitance here. We define that voltage is VR, and that voltage is VL, and that voltage is VC. And this is 100 microfarad and 20 millihenry, and this is 10 ohm. So let VST is sinusoidal. The variable is magnitude is 100, and cosine omega is 1000. Here we can rewrite omega is 1000. Then we need to do is verify the complex power is conserved. That means all S is 0. So what should we do? To do that, we need to do is to calculate each power from source and resistors consumed by resistors and inductors consumed values and capacitor consumed values. So to do that, at first, what should we do? We need to calculate the current phase. So the current phase is V divided by Z. Then what's Z? Z is GR plus GL plus GC. And GR is 10 plus GL is J, omega is 1000 and 0.02. And GC is minus G 1000 and 100. Okay, we need some space. Microns here is here. So the value is 10 plus J20 minus J10. So therefore that is 10 plus J10. The written is polar form is 14, 4, angle is minus 45 degree. So V was 100 and impedance is 15.14 and 45 degree. Therefore current is 7.07 and minus 45 degree. Now let determine the VR. What is the VR? VR is GR and I. And GR is 10 and I is 7.07 and minus 45. Therefore 7.7 and minus 45 degree. And what is GL? VL is GLI. And GL is J20 and I is 7.07 minus 45. So that will be 20 and 90 degree and 7.07 minus 45 degree. So the result is simple. 141.4 and angle is 45 degree. And VC is GCI, and GC is minus J10 and I is 7.7 minus 45. Then result is 10 and minus 90 and 7.07 minus 45. The result is 70.7 and angle is minus 135 degree. So we are ready to calculate each component complex power. At first, we calculate complex power of the source. That is half and Vs and I conjugate. Then that is half Vs is 100 degree and current is 0.07 and actually minus 45 but conjugate, therefore plus 45 degree. So then the result is 353.5 and 45 VA. So that can be represented in the polar form 249.96 plus J 249.96 is VA. This will be P and this will be Q. Then what is a SR? Is a resistance complex power. That is same way half VRI conjugate. This is half VR is, shall we calculate here? This is a VR. So we write here 70.7 minus 45 degree. And what is the current? Current is, this is current. Current. So conjugate here. Therefore 7.047 and 45. So that value is 249.96. This is actually power consumed by resistor, and no reactive power because this is a resistor. And SL, the same approach, is 1/2 half VL I conjugate. Half VL is here. This is VL, so 1 4 and 45 degree, and count is 7.07 and minus 45, but conjugate the plus 45 degree. Then result is 590 degree. So that will be Jane 500. So what's the meaning of that? This is a Q. And how about composite power capacitor? The same, half VCI conjugate. Half VC was here, so that will be 70.7 minus 135 degree, and conjugate is 7.07 and 45 degree. Then result is minus degree. So there will be minus say 25. This is another Q. Is C. This is L. Therefore, the consumed by impedance RLC is S impedance is SR SL SC is and supplied from the source is that value. So there will be conjugate here because this is the same things. I mean, I want to show you something here. Actually, active power is supplied from the source, so they are consumed in the register here. That's okay. But actually, source supplied reactive power is 250. But how about the inductors? This is a 500, and capacitor is minus 250. So that means inductance need to 500 the reactive power, but half of them is supplied from the source, and the remainder, the half, is supplied by capacitor, because the power angle in power page is difference in capacitor and inductors. So anyway, the supplied from the source, the composite power is exactly the same is consumed by the impedance R, L, and C. Therefore, composite power is conjugate.